Professor Bates, it's over to you.
No.
Thanks, Elna.
Okay, so I would like to thank PHT for giving me this opportunity and for asking me to talk about this topic and to give a bit of background before we start with all the detailed presentations. And then, of course, because I am a microbiologist, I will be focusing on the microbiological considerations during freeze thawing. Now, we cannot talk about thawing because it's inexplicably, or not inexplicably, it is obviously linked to freezing. We I would like to just start there at the freezing process. So, freezing has been a key technology. I don't know, I seem to have a bit of a problem here. So freezing has been a key technology in bringing convenience foods to homes and restaurants. And it causes minimal changes to the quality of food in terms of the size and the shape and the color and the flavor and the microbial load of the food. Freezing is a method of preservation that we are all familiar with, and we know that the microorganisms are actually prevented from multiplying by application of these temperatures. But because the process does not kill all the types of bacteria, those that survive and revive in the thawing foods and can also grow more rapidly than before freezing. We may also be aware that during freezing, a proportion of the water in the food changes from a liquid to solid to form ice crystals, and therefore this lowers the water activity. What is also important to know during freezing is that the enzymes in the frozen state remain active, although at a reduced rate, and this becomes more important later on when we discuss the effect of thawing. So freezing does, however, cause the water in the foods to expand and tend to disrupt the cell structure of the cells by forming ice crystals. And then if we have quick freezing, the ice crystals are smaller, producing less cell damage than with slowly frozen products. Freeze-thaw stability is one of the important physical properties of a substance relating to its ability to undergo freezing and subsequent thawing without damage to its structure or properties. So this is one of the most important ingredient qualities of a foodstuff that we will be freezing and subsequently thawing. We are all quite familiar with the foods that are generally frozen, shown in the slide, like fish, baked good fruits, vegetables, prepared food like pizzas, and then all types of meats, processed meats, and so on. Now, freezing, we know, that is why we use it, prolongs the shelf life of products by slowing the microbial growth and the enzyme activity. In general, the lower the temperature of frozen storage, the lower the rate of microbiological and biochemical changes. However, freezing and frozen storage do not inactivate the enzymes and, as I've stated, have a variable effect on the microorganisms. The negative effect of freezing on the microorganisms is due to the temperature shock, the concentration of the extracellular solutes, the toxicity of the intracellular solutes, dehydration, and ice formation. Now, it has been found and it has been stated in literature that quick freezing and thawing would result in higher microbial survival rates than those found with slow freezing and thawing. So relatively high storage temperatures between -4 and -10 have a greater lethal effect on the microorganisms than do the lower storage temperatures between -15 and 30 degrees Celsius. Different types of microorganisms also vary in their resistance to low temperatures. Other factors that affect the microbiological quality of the frozen foods are the physical and chemical characteristics of the product, the pre-freezing microbiological quality, and the extent of handling during and after freezing. So quite a number of factors that one needs to take into account. The question is, are we always aware of those, and do we take them into account? So when frozen food is thawed using air or water, the surface ice melts to form a layer of water. But water has a lower thermal conductivity and a lower thermal diffusivity than ice, and the surface layer of water therefore reduces the rate of which the heat is conducted to the frozen interior. This insulating effect increases as the layer of thawed food grows thicker. In contrast, during freezing, the increase in thickness of ice causes heat transfer to accelerate because of the higher thermal conductivity of the ice. Thawing is therefore a substantially longer process than freezing when the temperature differences and conditions are similar. So during thawing, the main considerations in thawing are to avoid overheating the food, to minimize thawing times, and to avoid excessive dehydration of the food and drip losses. And in the first slide that Linda showed, in looking at the changes that we now have to take into account in terms of the regulation, you can see many of those actually relate to this statement. So in the home, we'll find that mostly food are thawed using small temperature differences with a prolonged thawing period. And commercially, foods are thawed in vacuum chamber by condensing steam, or by warm water, or by moist air that recirculate over the food. I found this interesting review on food thawing technologies, and it's open source online. And I thought I'd just sensitize you towards this, so that if you are interested in food thawing technologies, you can just look for it and download it and read it. And in this paper, they actually have reviewed 53 published papers, and there's a nice heat plot of the food materials when novel thawing technologies are shown for various products. And this could be quite an interesting resource related to thawing. So when we look at the changes to foods during thawing, the changes we will experience, or the food will experience, will depend on the speed of thawing and the time that the food is held close to its freezing point. The changes to the foods also depend on the rate of freezing and the temperature, and possibly temperature abuse during storage, which determines the damage caused to the cellular structure and hence the amount of drip loss on thawing. For these reasons, it is important to note that thawing is not simply the reverse of freezing. And this must be included, therefore, in your food safety program or your GMPs. It must be considered fully in terms of critical control points and control points. I think I have now gone forward a bit, so let me just go back to where I was. Sorry about that. Let me get to my slide that I'm looking for.
You're good.
Okay, so drip losses is one of the changes that we will get in food. And for example, in beef, the losses can be, in terms of vitamins, can be up to 12% thiamine, 10% riboflavin, 14% niacin, and 8% folic acid. And in fruits, we can lose up to 30% of the vitamin C. So drip loss also forms substrates for enzyme activity. Coming back to what was initially stated, that freezing does not eliminate enzyme activity totally, and microbial growth. So microbial contamination of foods before freezing caused by inadequate cleaning of the food and inadequate blanching will now come back and will have a pronounced effect during this period, permitting the growth of psychotrophic spoilage and pathogenic microorganisms. Now, some frozen foods are cooked before consumption to a temperature that is sufficient to eliminate the microorganisms. But we have other products like cream and frozen cakes that are not cooked, and we should therefore be they should be consumed within a short time after thawing. Now, it is possible, and it was mentioned in the introduction, that one could experience, there could be temperature abuse during the thawing period. Now, in practice, temperature abuses in the cold chain could have a negligent impact on the microbial quality of the food as long as the food remains frozen. However, if thawing or partial thawing occurs, you will have microbiological problems. So in most cases, or in many cases, temperature abuses do not result in complete thawing. If this is the case, then one must be careful to investigate or check the microbiological quality of your product. And of course, other quality parameters like the appearance and taste need to be assessed. So the number of microorganisms is reduced during freezing and frozen storage. Also, the bacteria will remain in the lag phase for some time after thawing, and this is exactly what we would want in terms of the shelf life of our products. But the freezing may affect the structural integrity of food, making it more susceptible to microbiological attack. So I think you can start to see that thawing is actually a more complex process than one would normally think. So in terms of the lag time of our bacteria, if we thaw below minimum growth to 1 to 4 degrees Celsius, we could expect, depending on the product, a lag phase of 2 to 3 days, and also depending on the initial microbial quality. But if the thawing temperature is above 5 degrees Celsius, we cannot expect a lag phase before exponential growth, and then this will obviously affect the shelf life of your product after thawing. Now, freezing may affect the structural integrity of the food, as I've stated, and make it more susceptible to microbiological attack. Thawed foods may have a moist surface due to drip or condensation and may be a very good substrate for the bacteria. In addition, some of the bacteria in frozen fruit may become more virulent after thawing and the lag phase. The conclusion of most studies on thawed foods, and there are actually not many studies that look at the thaw process itself. Most focus on the freezing aspect, is that there is very little difference in the shelf life and microbiological load between the unfrozen and thawed foods. So if the process is controlled and everything is done as it should be, then this is what we can expect. As with freezing, the rate of thawing also influences the number of microorganisms that are able to survive. So we may expect higher recoveries with faster thawing and freezing. And the reason for this is because faster thawing prevents the formation of bigger ice crystals. In the course of thawing, as the temperature rises, the ice crystals grow and affect the integrity of the cell membrane. Therefore, subsequent damage may result, including the leakage of water and materials with low molecular weight, the increased penetrability of certain enzymes, and the increased sensitivity of the cell to certain compounds. Consequently, the freeze-thaw process stresses the bacteria and thus result in the increased sensitivity, increased lag phase, decreased generation time, and decreased growth rate of the bacteria. If we look at food spoilage due to the microorganisms, the thawed food may spoil faster than its fresh counterpart. This is possibly due to textural changes from freezing and thawing, which may help the surface organisms enter deeper into the components of the food and facilitate the spoilage process more quickly and thoroughly. Also, water condensation and water-soluble nutrients that appear on the surface of thawed foods may help the spoilage microorganisms grow faster. So also something we need to take into account is that our freezing and frozen storage may eliminate our mesophilic and our thermophilic organisms in the matrix. And therefore we will possibly have a less competitive environment for our psychotrophs, and therefore their growth might be enhanced during thawing and subsequent shelf life. So this is an interesting study that I found, the detail given here is just to say that this is a predicted value. So it is not a experiment conducted in a laboratory, but this researcher used modeling. And it just shows the predicted lag phase in hours for Listeria monocytogenes, and I couldn't really find anything in terms of actual experimental data, but modeling is used in the industry to give us predictive value. So, and what's interesting here is that here we see crab meat, corn, green peas, and shrimp. And if we just look at the predicted lag phase for Listeria monocytogenes in these products, you can see how it would vary from 3 hours at 4 degrees to 19 hours for shrimp. So the type of food that you are actually thawing needs to be taken into account in relation to the microorganisms that you are expecting in your product. And then the same researcher used the predicted values and then compared it to the days that until the product would become unacceptable. And what's interesting here is at 4 degrees Celsius, in terms of they found 10 days before the product becomes unacceptable, but the predicted growth of Listeria monocytogenes is already 3 log, and shrimp it would take 6 days with predicted value 1.7 log. So I think what I would like to convey with these 2 slides is the understanding of one's own product in terms of the parameters given here is, do you understand what will happen to your product during thawing with the possible pathogen that you, the risk pathogen that you have identified? Now, we spoke about resuscitation of the cells within the food matrix. So these cells that have been injured during freezing, we can expect a repair of these cells with appropriate recovery conditions if they are in the presence of essential nutrients. They can then regain all the normal characteristics within several hours of resuscitation. Within several hours, if the resuscitation occurs properly. The recovery occurs during the lag phase of the microorganism's growth. So hence, we want to extend the lag phase as long as possible. So in the laboratory setting, one would use non-selective media to ensure the recovery of both the injured cells and the uninjured cells. And this would be important in terms of describing what happens during the thaw process of a particular product. And as has been said before, we know that freezing can cause extensive damage to the microorganisms, but the food matrix is much more complex than laboratory media. And what is actually needed for resuscitation of the microorganism in food matrix is not well known. We do know that cryoprotectants such as sugar, amino acids, peptides, and glycerol in food may help the microbial cell functions to return to their original state. So, in conclusion, the presentation has indicated that the microbiology of frozen foods is not very different from the microbiology of chilled foods. The frozen foods have the great advantage that the microorganisms do not grow in them when the food is in the frozen state. However, the degree of monitoring of safety is the same as in the production of chilled foods. So our HACCP system, our food safety systems, that should all reflect the related critical issues in terms of freezing a product. What is also important is that thawing would be a control point, and depending on the product, possibly a critical control point. It must be ensured that the thawing process is appropriate with regarding to minimizing the microbiological growth during thawing and afterwards. Although it is clear that in optimal conditions, the microbial growth in thawed food is the same as in chilled foods, this is what we mostly can expect. But this is not really a view that is considered by most researchers. And the reason, I think, is that there isn't enough scientific information or scientific work that one could look at to conclusively say. And therefore, conducting more experiments in this field seems necessary, although regarding the quality and shelf life of thawed foods. So I hope this presentation has given you a bit of insight into how complex actually that thawing process is. Yes, the question is, do you understand what's happening during thawing with your project, with your specific product? Thank you.
Thank you, Professor. I think that there's a couple of scary words. I get really worried when you start to use the word resuscitation and microorganisms in the same breath, because, you know, the thought that you could literally have something coming back to life again is very, very concerning. But I think that's exactly what you're saying to us. You're saying that we need to understand that Although the microorganisms may be damaged during the process of freezing, it doesn't mean that they're damaged for good. It's not that they're going to die during that process. Am I understanding you correctly?
Yes, Linda, and it's clear that there are definitely parameters in where one would extend the lag phase and where the shelf life would be similar to chilled foods. But there are also issues in terms of temperature abuse, and as had been stated earlier in the introduction, what's happening on the floor, what we see every day, will that actually enhance your the shelf life of your product after thawing?
Absolutely. So just for the non-microbiologists amongst us, because I know that we've got a number of people that are coming in from industries that are maybe more food service related, so maybe not as many technical people on the floor. The lag phase is obviously the phase where the microorganisms are not actively reproducing. So if I understand correctly, and I'm trying to put it in as simple terms as possible, we have almost a static population at that point in time. In other words, there's no growth, there's no multiplication. But as soon as we hit the magic 4 hours or whatever it was on that study, then we hit the go button, and then we start to make babies, and that's when life gets really interesting. Am I correct?
Yes, so actually controlling the thawing process and the temperature during thawing is extremely important. And if we look at the statement also that you may be affecting your mesophilic and thermophilic bacteria, and that the psychotrophic bacteria are those bacteria that actually grow between 7 and 25 degrees Celsius. So these are typically the bacteria that will cause spoilage, for instance, in your meat products and in milk. So because we are also affecting some groups which do not survive frozen storage, we are basically giving those bacteria almost a head start during thawing when we are releasing nutrients, and they can then start multiplying. However, bacteria do have a lag phase. So this is the time when the bacteria remain static. So when they do not grow actively. And the whole mission in the food industry with bacteria is to keep your bacteria in the lag phase. So everything that you do is to make sure that these bacteria do not start growing. Once the bacteria start growing and go into what we call the exponential phase, there is almost nothing that you can do to reduce the multiplication of bacteria, of this group of bacteria in your product, and this then directly affects your shelf life.
Absolutely, and I think that's really important. So we may be talking about food safety, but what you're really highlighting is the importance of the quality of the product, because spoilage organisms are going to have a direct impact on the quality of the food that you're preparing. Let's not throw money away by abusing this step at the end of the day. So I think for the audience, you now know exactly what happens to those chops that you put in the sun before the braai. And I think we all fall into this very, very bad habit of abusing product when we forget to take it out in time for it to thaw properly.